The second topic that I want to talk to you about in this class is the idea of connectivity of a graph. Before being able to represent or to discuss what connectivity is, we need to introduce two initial definitions of a path and of a circuit. Now, in the lecture notes, you have the mathematical definition of it, but let's go through an example which makes it quite clear. So I have at the bottom a simple undirected graph, and in red I can see a path. A path is simply a sequence of edges such that they are basically one next to each other. So I have a path A which consists of the edges AB, BC, and CF. So one between two edges that are next to each other, there is a in this sequence of edges, there is a vertex in common. Now a circuit, it's a path with the additional property of starting and ending at the same point. So in blue I have a circuit. I can see, for example, I may choose A as the starting point, and I have AE, ED, DA. So it goes through the same sort of sequence, through a sequence, and it gets to the starting point. Similarly, I can also define paths for directed graphs. Now, as we should be aware by now, a directed graph has a directionality associated to it. And of course, in a path, in a directed graph, I must follow the direction of the edges. I cannot go through an edge in the opposite direction. Now, paths are actually used in practice in many scenarios. So let's consider, for example, a friendship graph where people are vertices and an edge connects two people if they know each other, for example. Now, something that has become very famous in culture is the idea of 6 degrees of separation that basically tells us that we are almost connected to anyone else on Earth by a chain or a sequence of 6 people, which means that there is a path of length 6 connecting us to any other person in the world in a friendship graph of the whole Earth population. Here in the slide you have also some other famous numbers that can be associated with paths of graphs that, for example, you may look on Wikipedia what they actually are if you are interested in it. Now, having defined paths, it actually allows us to define what a connected graph is. Now, an undirected graph is called connected if there is a path between every pair of distinct vertices of the graph. So there is, what this tells us is that I can go through a path from any pair of vertices in a graph. Now, even for graphs that are not connected, we can somehow measure how connected they are via the idea of a connected component. So this is a subgraph of the graph, which is connected and is not a subgraph of another connected subgraph. Now, it is simpler to actually show it with a graph. So here I have a graph with 8 vertices, 3 that I colored in red, 2 in blue, and 3 in green. And I have some edges. Now, what I see is that the graph is not connected because there is not, for example, a path from a red vertex to a green vertex, or a green with a blue, or a blue with a red, and so on. And in particular, with the color, I denoted the connected components of this graph. These are subgraphs which are connected, and also there is not a bigger subgraph that includes, which is still connected. So, for example, if I were to consider the two leftmost vertices, those two in red, one over the other, that would not be a connected component. Why? Because there's also the third red vertex in the middle, such that by also including that vertex, I still have a connected graph. So just the two vertices on the left is a subgraph of a connected subgraph of G, and therefore is not a connected component. The three red vertices are a connected component. So now the idea is, okay, I can define when a graph is connected and when a graph is not connected. But how connected is a graph? So, for example, let's suppose I have a computer network or a transport network, and knowing that the graph is connected tells us that any two computers can communicate or that I can go from A to B in a network. But also we would like to know how reliable the network is. What happens if a computer breaks down? Or what happens if a connection between two computers breaks down? So the idea is, okay, what if I were to drop some part of my graph? Would the graph still be connected? So these are the next definitions that we will give. So a vertex whose removal, together with the removal of all their incident edges, produces a subgraph with more connected components than the original graph is called a cut vertex. Or an edge whose removal produces a subgraph with more connected components than in the original graph is called a cut edge. So let's look at the graph at the bottom to give some ideas. Suppose let's start with edges, which are slightly simpler. So if I were to remove the edge between F and G, then you would see that we have two connected components. So the removal of the edge FG creates a graph which has more connected components than the original graph. Similarly, this happens for the edge AE on the left. Conversely, if I were to delete the edge, say, DG, then my graph would still be connected, and therefore DG is not a cut edge. Let's consider next cut vertices. Now, when I remove a vertex from a graph, I do not simply remove the vertex, I also remove all edges incident to it. So let's suppose that I were to remove the vertex A. If I remove the vertex A, I also need to remove the edge AE. But then if I were to remove all this, my graph would still be connected, and therefore A is not a cut vertex. On the other hand, if I were to remove the vertex E, I would also again remove the vertex EA, but in this case then A becomes isolated. There is no edge connecting A to all other vertices. Now the graph has two connected components, which is one more than in the original graph, and therefore E is a cut vertex. So in red here I denoted the cut vertices that you can identify in this graph, and in blue I denoted the cut edges. So a connected graph without cut vertices is called non-separable. So the idea is here, okay, we may not simply consider the deletion of a vertex, but we could also consider what if I were to drop a subset of the vertex set. So a subset V prime is a vertex cut if G minus V prime is disconnected. Also, the idea is, okay, maybe there are no cut vertices. Then how big does a vertex cut needs to be in order for the graph to become disconnected? So the concept is what we call vertex connectivity, that we call kappa G. Now, the vertex connectivity of a graph is the minimum number of vertices in a vertex cut. So the larger kappa G is, the more connected G is, because I need to choose more and more and more vertices in order to disconnect the graph. Now here there are some definitions and some properties of some special graphs that I do not want to focus on right now. But similarly, we can also define edge connectivity. So first we define an edge cut as we define the vertex cut, which is a subset of the edge set, such that by deleting those edges, the graph becomes disconnected. The edge connectivity of a graph G, denoted by lambda G, is the minimum number of edges in an edge cut of G. Now, an important thing to notice is, okay, if I have a edge, if I have a vertex, and I delete all edges that connect that vertex, then I know that my graph becomes disconnected. So this actually gives us these two inequalities for lambda G, but also for kappa G, which tells us that the maximum vertex connectivity and the maximum edge connectivity, or well, the actual number of the vertex connectivity and the edge connectivity has to be smaller or equal to the smallest degree in the graph. The other thing is, in general, vertex connectivity is bigger or equal, edge connectivity is bigger or equal to vertex connectivity. Let's look at an example. So here I see that I have a connected graph and that all vertices have degree at least 3. So for example, A is connected to B, G, and F, B is connected to A, G, and C, and so on. So I know that vertex connectivity and edge connectivity are at most 3. So the idea is, can I delete any vertex and obtain a disconnected graph? If so, then vertex connectivity is 1. Or can I delete any edge and obtain a disconnected graph? Then edge connectivity would be 1. If the answer is no, then if there are pairs of edges or pairs of vertices that disconnect the graph, then vertex or edge connectivity are equal to 2. Otherwise, this must be equal to 3, because we know that at most it is equal to the smallest degree of any vertex. So let's start with edge connectivity, for example. Now, we see that sort of the right-hand side of the graph is a lot more connected. So probably from the right-hand side, there is nothing we can really do to disconnect it. Now, sort of the part between vertices B, C, G, and F seems to be the one with least connections. But notice that by simply deleting, there are no two edges that by themselves would make the graph disconnected. So it may look like that, for example, by deleting edges B and C and G and F, I make the graph disconnected. But there is still the edge AF that connects the two sides of the graph. So, for example, a vertex cut is the set AF, GF, BC, because then ABG is a connected component and CDFE is another connected component. Notice that this is not the only edge subset of the edge set that is an edge cut with 3 elements. We could also delete AB, AG, AF, and then A would be isolated. So those would be an edge cut. But in blue, you can see one of them. On the other hand, for vertices, again we see that by simply deleting any vertex in our network, the graph would still be connected. So we need to look at pairs of vertices. If I were to delete vertices B and G, then I would also need to delete all edges incident to those. But we would see that A is still connected to C, D, F, and E, because there's the edge A, F, which would not be deleted. So the deletion of B and G doesn't create two connected components. On the other hand, the deleting the edges C and F creates two connected components, one with A, B, and G, and the other with the vertices D and E. And that's why C and F is a vertex cut. And therefore, vertex connectivity is equal to 2 for this graph. Now, there is also the idea of connectedness in directed graphs, which I will skip for the sake of this video.